Arun Majumdar from the University of Stanford in California. And we just wanted to say a few words that this series is designed to connect faculty and students in all areas of nanotechnology to promote a forum for discussion and the latest trends and developments in this constantly evolving field. Each term, WIN will plan to host at least one Research Day symposium in each of the 4 key theme areas of nanotechnology, specifically smart and functional materials, connected devices, therapeutics and theranostics, and today is our next generation energy systems. To open the workshop, I would like to invite our distinguished Associate Vice President International for the University of Waterloo, Professor Ian Romans.
Thanks very much, Lisa, and delighted to be with you here today, and you've got an exciting agenda in front of you, most definitely. And I'd like to begin by inviting you to reflect as we honor the land and the indigenous heritage of this place, which date back more than 10,000 years. I'd like to acknowledge that the University of Waterloo and surrounding areas are located on the traditional territory of the Neutral, Anishinaabe, and Haudenosaunee peoples. The University of Waterloo is situated on the Haldimand Tract, the land promised to the 6 nations. That includes 10 kilometers on each side of the Grand River. Indeed, the events today in front of you at the Waterloo Institute for Nanotechnology here at the University of Waterloo are very exciting. And as I was looking over the agenda and reflecting upon the themes you're going to advance, I thought they spoke very much to the kinds of things that the University of Waterloo is doing across this campus. And kudos to WIN and its leaders for delivering them to you today. For one thing, the importance of innovation is clear. WIN's at the forefront of the ways in which science and engineering are undergoing activities at the atomic scale and making important contributions. And when I see your agenda in front of you and I see issues of investigation with regard to energy storage, solar cells, and others, I really understand that you are pioneers with regard to making important contributions to society in terms of basic science, basic engineering, and contributions to well-being as well. Interdisciplinarity is another theme that's being emphasized at the University of Waterloo, and again, kudos to the organizers for what they've put together today. You've got 9 research presentations, and by my count, your presenters come from 5 different units at the University of Waterloo. And you've got a panel at the end of the day where you've got representatives from different faculties, from different research centers, and from different sectors of society as well. For a range of what are called complex or sometimes messy issues, we need, many argue, different perspectives to be brought to bear. Energy is one such of those issues. And indeed, what better way, well, what good way to bring different perspectives to bear than to have internationalization. And when you bring in new ideas from beyond our national borders, when you go out into the world and get to experience new insights, hear new insights, and experience new ways of doing things, we can all be enriched. And it's wonderful that WIN's following what it does naturally, which is its internationalization agenda. It's been a pleasure to work with its leaders on a range of international files. We've got today a distinguished lecturer who is coming to us from outside Canada, and he will be introduced to you more fully in a few moments. So my last words, I'll just say 3 things, 3 messages for you. My first message is congratulations to the organizers and to all of you for accepting the invitation. You're doing really important work. Energy well-being energy sustainability is critical in the world today. The billions of people need a safe and secure and sustainable means of getting energy services. So well done for your important contributions to scholarship and society. A second message is a welcome to all of you for your day, or to the day's events today. I was going to say a special welcome to those of you who are here from outside of the University of Waterloo, but then I thought, well, my Waterloo colleagues are special as well. So I'll say a different kind of welcome to anyone who has traveled from outside of Waterloo to be with us here today. We're hoping that you will get some ideas for collaboration and that there may be a few connections that you're able to sustain after you go home as well. And third, success and enjoyment today as well. Success, billions of people are counting on everyone who's doing work in the energy area. and enjoyment, because it's been my experience that as we need to have societal positivity in order to get transformative breakthroughs. So thank you very much for the invitation to speak. I wish you all the best for today. Thank you.
Next, I'd like to invite WIN Executive Director, Sushanta Mishra.
Good morning, everyone. It's a real pleasure to have Arun Majumdar from Stanford to be part of our thematic research day event, which is focused on next generation energy system. This event is possible because of extremely hard-working leads and co-leads of the team. So I have Michael Pope here, who is one of the co-leads, Linda Nazar, who is the lead for the thematic area, as well as Ehab, who worked hard to put together this program on behalf of the thematic, behalf of the theme, which is the next generation energy system. It's an exciting program all throughout the day, which is concluding with the panel discussion, and hopefully you'll all enjoy, be engaged with the panel, and we look forward to a very exciting and engaging day for everyone. Thank you so much for joining us here. Thank you.
Okay, and on behalf of the research faculties and specifically the Faculty of Science, I'd like to invite Associate Dean of Research, Dr. Shirley Tang.
It's my great pleasure to be here, and with two great speakers ahead of me, I don't think I have much to say. Next generation energy systems is certainly a top research priority for the Faculty of Science, and this type of multidisciplinary symposium with specific research aim is definitely very exciting. I just want to say thank you to the WIN office for organizing this event, and I hope you all enjoy exciting discussions and presentations and get on to with more wonderful work. Thank you.
I would also like to re-invite Dr. Mishra to introduce our distinguished lecturer.
Good morning, everyone. It is my distinct pleasure to welcome Professor Arun Majumdar as the WIN Distinguished Speaker as part of our inaugural Research Day Symposium, Next Generation Energy Systems. Dr. Majumdar is J. Precourt Chair Professor at Stanford, also a faculty member at the Department of Mechanical Engineering as well as Material Science and Engineering, and is the co-director of the Precourt Institute for Energy, which integrates and coordinates research and education activities across all 7 schools and the Hoover Institution at Stanford. Dr. Majumdar's research in the past has been involved with the science and engineering of nanoscale materials and devices, particularly in the areas of energy conversion, transport, storage, as well as biomolecular analysis. His current energy research focus on using electrochemical reaction for thermal energy conversion and various ways of looking at carbon-free hydrogen and other issues related to energy, particularly a new effort to re-engineer the electricity grid, which I believe we'll be talking in this distinguished lecture series. In October 2009, Dr. Majumdar was nominated by President Obama and confirmed by the Senate to become the founding director of the Advanced and Research Projects Agency Energy, which is acronym as ARPA-E, where he served till June 2012 and helped ARPA-E to become a role model for excellence in government delivering energy policies and program across various institutes and stakeholders. Between March 2011 and June 2012, he also served as the acting Undersecretary of Energy, and he held a number of key positions in the government, including some such as the senior advisor to the Secretary of Energy, Steve Chu, as well. He has a distinguished career of academics as well as has received a number of distinguished awards, including is a member of the National Academy of Engineering and the American Academy of Arts and Science, among many others. It is my distinct pleasure to invite you here at Waterloo. I believe this is the first time you are in Waterloo, and we hope to see you more often coming to Waterloo and bridge the relationship relationship between Waterloo and Stanford. Thank you so much.
Well, thank you, Sushant, for the very warm welcome, and thank you all for inviting me out here. Can you hear me at the back? Someone was, I think Shirley was telling me that the weather is really bad out here and apologizing for it. Let me apologize for the bad political weather back in the United States, and I'm happy to be here. So I'm going to talk about energy, and the title is, of course, Turbulence. And as you know, turbulence is a bumpy ride. And I would say the next 20, 30 years is going to be a bumpy ride. And I'm going to explain that. But this, let me start by saying, I wish I was a freshman undergraduate student today. Not because I want to be 40 pounds lighter, which is then look like these guys, but frankly, the next 40 years is going to be the most exciting period in the field of energy. And so to really appreciate what the future holds for us, I want to take you back in time. And as you know, about 250 years ago, when the founding fathers of the United States were fighting a revolutionary war, there was another quiet revolution taking hold in our society across the world. And that quiet revolution is what we now call the Industrial Revolution. And the Industrial Revolution was so transformative that it brought a quality of life and prosperity in our lives that George Washington or any of the founding fathers, at least in the United States, would have never imagined. I mean, today we live in very well-lit and air-conditioned homes, and we sit in our living rooms, watch Usain Bolt run in the Olympics. Could not have been done 250 years ago. Our life expectancy has gone up by a factor of 2 since the beginning of the Industrial Revolution. We have, this thing is not quite working, amazing healthcare and high-speed travel. This is how we used to travel 250 years ago. And this is how, in horses, and maybe not 1 horse, maybe 10 horses, maybe 20 at the most. We can fit 100 horses in the engine of a car for a grocery store. Or we can put 100,000 horses in an engine of an airplane and travel around the world in 24 hours that would have taken months. This is absolutely spectacular, remarkable period of human history, and a short period where things have gone exponentially well. And at the foundation of this all is energy. You take energy and everything falls apart. And so energy really shaped the 19th century and 20th, maybe not 18th, 19th and the 20th century. And it is so embedded in our lives now that access to affordable energy is a matter of national security. That's how deep it is. And so if you look at this picture, you realize the Industrial Revolution was going from horsepower to horsepower. That's what it's all about. And yet, despite all this enormous success, the next 20, 30 years, or this century, it's going to be different. And what happens now will shape the 21st century, not only the economic growth around the world, it will shape the environment, it'll shape the international security and geopolitics of the 21st century. That's how important this is. And the question is, why? What is going on? I mean, we are at the threshold of an even bigger transformation, nothing short of a new industrial revolution, of an industry that is on the size of about $10 trillion. The debate is it 10 or $30 trillion? We'll take an average, $20 trillion. That is enormous. It is the second largest industry compared to healthcare around the world. And that is going through a fundamental shift. So what is going on? I'm going to say a few game changers, introduce them to you. One of them is quite familiar. The first game changer, I don't think this is working very well. The first game changer is unconventional oil and gas. 30 years ago, this was an outlandish idea, horizontal drilling and hydraulic fracturing, and 30 years of persistence R&D as well as implementation, and this is a game changer. It has changed the global landscape of oil and gas. North America is now energy self-reliant. It doesn't need energy from elsewhere. United States has become the largest exporter of natural gas. It is the abundance of natural gas and the low price of natural gas has reduced the cost of electricity around the North American region. It is bringing back and reviving the chemical industry, which had gone to Asia. And this is all because of cheap and abundant natural gas. And we are likely to see a huge amount of LNG trading that's going to happen around the world. The global implications of natural gas is so profound that we don't really appreciate the full implications of that. So I'm going to tell you what's going on at Stanford. At Stanford, we've just started a natural gas initiative to really research all the aspects of unconventional revolution, including the environmental impact of methane emissions, et cetera, which is a really important thing, for which we need sensors, distributed sensors, or satellite imagery, et cetera. So this is game changer number one. It has really changed everything in the world of oil and gas. Game changer number two is lithium-ion batteries. Over the last 10 years, the cost of lithium-ion batteries has come down by a factor of 5 to 6, which we never quite expected when we were in the Department of Energy. We were investing a lot in this. But it's come down to the point that in the next 5 to 7 years, we can see the glide path of bringing the cost of a battery pack down to $100 a kilowatt hour. What does that mean? At $100 a kilowatt hour, the cost and range of an electric vehicle will reach parity with gasoline cars without subsidies. You don't need any government subsidies then. And you give it another 5 to 10 or about say 15 years or so, you will see deep penetration of electric vehicles around the world. This is a tectonic shift for an auto industry which for the last 100 years focused on gasoline-based automobiles. This is a complete tectonic shift. And you add to that mobility services and autonomous driving, and we are seeing a colossal paradigm shift in the mobility space. That's where we are today. Okay? And there's still room, plenty of room for innovation. Now, one of the big challenges is the following. We are today at about 5 million electric vehicles in the world. It's increasing, but around the world there are 1 billion vehicles, cars, buses, etc. So that's a long way to go. But the next 15 years is going to be game-changing. Now, here's the challenge. Whenever you want to drive an electric car, you need to charge, you need the electric grid. The electricity sector never had to talk to the auto sector in the past. Now they have to. The electricity sector is often regulated, where the prices are fixed, retail prices. The auto sector is unregulated. There is no price fixing. On the other hand, the auto industry had to respond to fluctuations in the global oil price or fuel efficiency standards. Electric vehicles have none of that. This is a transsectorial game changer. not just one sector. And when you have 5% penetration of electric vehicles like we have in California, everyone's proud of it. We've got lots of Teslas and Nissan Leafs and all that. 5%, it's reasonably easy to look for EV charging, except perhaps in a Google campus. At more than 50% penetration, it is like you going in an airport trying to look for the outlet to charge your phone. Okay? That's the problem that we're going to have. And we need to figure this out. This is a game changer in many ways, and that's all mostly related to lithium-ion battery cost. And innovations in materials and nanostructuring has really changed the ballgame in this. This is game changer number 2. Game changer number 3, modern renewables. The cost of renewables has come down by a factor of 6 to 7 in the last, again, a decade, to the point that electricity generation from wind and solar is the cheapest way to produce electricity of all sources. And the investments that have gone on in solar and wind, been 70% of all the new investments that have gone on in the power sector is due to solar and wind. Okay? Even though it's still a small percentage, you can see that exponential, the early stage of an S-curve. You're seeing that happen. Hydro, I know Canada has a lot of hydro. Hydro is relatively flat around the world, but solar and wind is going like this. And here's the paradigm shift that is happening. The cost of electricity from solar and wind is undercutting that from coal, nuclear, and sometimes even natural gas. And when that happens, you realize that you have assets where you have trillions of dollars of prior investments that could become stranded assets, influencing not only the energy sector, but the banking sector, because they'll be defaulting. Talk about a financial crisis. That's the stage we're getting into right now. And we are seeing that happen not just in the United States, where coal is being undercut, not by any policy, but purely economics, but also going on in China and India. India has just invested about $80 billion in coal-fired power plants, and now there's a risk of being stranded assets right now. And the banking sector is going to be affected. This is the paradigm shift that we are seeing in the electricity sector. So if that's the case, these systems all have to connect to the electricity grid. All of these have to be connected to the electricity grid. We are still living in the paradigm and architecture of what we call the Tesla-Edison grid. And the Tesla-Edison grid, you have electricity going from generation to transmission to substation. This is the one-way power flow. Everyone knows this. These are large turbo machinery that generates electricity. It was never designed for renewables, fluctuating renewables. It was designed that if you turn on a switch over here, the generator had to turn on as well. So the switch, or you were the master, and the generator was the slave. It's flipping now. The master is now the generation because it is fluctuating. It depends on the weather. And the question is, will the demand side, will the switch become the slave? We don't know. So it was never designed for fluctuating renewables. So whenever you have fluctuation, you need some balancing. And the balancing can come from traditional sources, or it can come from hydro. Canada is very blessed. You have hydro, which you can do pumped hydro then. Or you could use some kind of storage, like natural gas is a stored energy. You could use that for balancing, or you could use batteries. The question is, how do you minimize, since you've already invested in all of this, how do you minimize the balancing? It's very important. And that minimization of the cost requires one to really evaluate this economically, which means evaluate it technically. It's science and engineering at the bottom. That's what we need to solve. So this is volatility on one side of the grid. Then there's volatility on the other side of the grid because of all these distributed assets of using, and these are heavy loads. And now you have a double whammy of uncertainty in the electricity grid. That's the grid of the future. And so the future of the grid is not just energy, it is synergy. How do you coordinate all of these so that the grid is stable, it is reliable, and it's affordable 24/7? We don't know how to do that yet. Fortunately, so you need some way to coordinate. Fortunately, we are surrounded by 50 years of the digital revolution, which Tesla and Edison never had. And so there's a real opportunity to connect the dots, to put a layer on top of the digital world where you collect data, you process data, you use it for control so that this is all affordable and as well as reliable 24/7. And this is the world that we are seeing right now. And so to enable this at Stanford, we started something called the Bits and Watts Initiative. Bits is for data, of course, watts is for electricity. And we use that to combine and thereby stabilize the grid when you have all these fluctuations and uncertainty going on elsewhere, everywhere. So, but this is just the start. There's a lot more to happen. The computing industry and the electricity industry never had to talk to each other. People talk about the smart grid. It's not very smart at all. We just collect the data. No one does anything with the data. We work very closely with all the utilities. We have to educate them what is data science? What is the digital world? This is what's going on right now. So this is what we are looking at. So if you really step back for a moment and you realize that all these game changes, we are encountering the confluence of multiple game changes happening, not one, not two, but 3 different game changes going on simultaneously worldwide. And I didn't even get time to talk about the 4th one, which is efficient LED lighting, which has brought light to those parts of the world that were using oil or kerosene for lighting in the past. So 4 game changes, and this is the remarkable part, 4 game changes happening simultaneously and at unprecedented speed, changing the world. Okay? This is the world we are entering. And if you think this is fast and this is a lot, think again. Because we need to go faster and farther. Why? Well, here's the reality. Going back to the Industrial Revolution and over the last 250 years, if we ask the question, what's your energy system like? We realize that the fuel mix is predominantly due to fossil fuels. So while we're very excited about the batteries and the EVs and the renewables, it is a small fraction of what we have. Mostly it is fossil fuel. 80% of the primary energy of the world is supplied by fossil fuels. We rely on fossil fuels on a daily basis. Any disruption to the supply chain of fossil fuels is a disruption to our lives. That's the world we live in. And yet we now know, and science has made it abundantly clear, that the use of fossil fuel leads to global warming. There's no question about it at this point scientifically. And the average temperature, the decadal averages, yeah, there's some fluctuations, but if you look at decadal averages, this is going only one direction. So how much temperature rise has gone on around the world? Well, the global average temperature rise is slightly more than 1 degree. And people say, oh, 1 degree, how does it matter? And that's where we scientists fail to explain it properly. And let me try to do that. The global average temperature rise is 1 degree. But the temperature rise is not uniform across the world. It is highly non-uniform. Let me explain that to you. Let me go to the poles first. You find that the temperature in the Arctic has gone up by, the air temperature has gone up by 3 to 4 degrees, not 1 degree. And because of that, the water temperature has warmed up. We have lost ice in the sea. The sea ice has gone down by 20%. It's only going in one direction right now. And if you think this is only sea ice, and by the way, a new ocean, you all know this very well, a new ocean has been created in the Arctic. Well, there'll be shipping lines going through. Within our lifetime, this is happening. And if you think it's only sea ice, look at the land ice. We have lost 4 trillion tons of land ice in Greenland and about 2 trillion more in the Antarctica. So this is affecting both the poles. And if you think this is only the poles, people say, who lives there? Well, this does cause sea level rise. And sea level rise by the end of this century is predicted to be 1 meter. By the end of the next century, 6 meters. Okay? That's the reality we are entering. And so this is, but people still say, oh, this is the poles. And so who lives there? Well, let me show you now the distribution, not the average, but the distribution over the summertime temperatures around the world. What is the distribution? Well, some summers are hot, some summers are a little cooler. Well, here's what the distribution looks like. Starting in the 90s and 50s, it's reddish, that's the hotter summers. But it's, fluctuating. And here's where it goes. These are the summertime temperatures. And you can see that it is reaching 4 to 5 times the standard deviation at about 1 million times the probability. Okay? That's the world we're entering. And if you think that this is only the global average temperature rise, okay, and so we're not quite sure exactly where this is going to go. And, how does it matter to me? Well, this is coming to a neighborhood near you. These are all-time high temperatures, happen only in the last couple of years, and this is only going to get worse. So the point I'm trying to make out here is that it is not the average that really affects you. It is the tail of the distribution that has a disproportionate effect on your people's lives, on people's health, on the agriculture, on livestock. It is the tail of the distribution that matters most because it is not just proportional to the average. Okay? And this is at 1 degree Celsius. So since I'm at a university, I'm going to give you a pop quiz. Okay? And I want you to, so don't worry, there's no grade. There are no grades in this. So I want you to think about, I'm going to show you some numbers, and I want you to think about what they mean. And then I'll give you the answer. Okay? So here we go. The first number is 1. Well, this is obvious. I just talked about it. This is 1 degree Celsius. And this is the global average temperature rise, 1 degree Celsius. And we realize, as I mentioned, that it is not the global average temperature rise, but it's the tail of the distribution that matters most. Okay? So we all agree on this? The second number is 2. What is that? Well, this is 2 degrees Celsius. This is kind of the agreement we thought we had, except for the United States pulling out in Paris. And if the tail of the distribution is 1 degree is bad, you can just imagine the tail of the distribution of the 2 degrees. It'll be very disruptive. And we said we should try to keep it below 2. Okay? That's the agreement we had. So this is 1 and 2. The next number is 800. This is not 800 degrees Celsius, don't worry. We're not living on Venus. What is this number? Here's the number. If we decide to keep the temperature, global average temperature rise below 2 degrees, then we have a budget of 800 gigatons of CO2 left. Okay? 800 gigatons of CO2. Since the beginning of the Industrial Revolution, we have emitted slightly more than 2,000 gigatons of CO2, and we have 800 left. The next number is 40. What is this? This is the rate of emissions per year, is 400 gigatons of CO2 per year, roughly. Okay? And the last number is 20. What does that mean? Well, you can do the math. If the emission rate is flat at 40 and we have 800 budget, we have 20 years left. Which is why I say this is really, it is the most exciting time and most turbulent time the next 20 years. I wish I was an undergraduate student right now because I want to solve this problem. And I want to give you the last number. If that's the equation, the last number is 0. Because after 20 years, it better be 0. And the Earth has to fit in to that 0. Okay? So for all the students out here, I want you to remember this math. It's very simple. And so if you think, a lot of people are extremely excited about wind and solar and batteries and all, and that is only a tip of the iceberg that we are trying to solve. The rest is this. So this is a huge risk to our whole global energy system. And so whenever we have risks, we take an insurance policy. If you have a risk of fire, you take in fire insurance, or flood insurance. This is, I can't imagine what this risk is like. So what's insurance policy? The insurance policy first is research. Why? Because we need new options. We need to reduce cost. This is only through research, or have a systems view to figure out where the gaps are, to identify those research topics. So having been excited about unconventional oil and gas and renewables and batteries and all that, this is all great. It is nothing compared to what we really need. So what else do we need? Well, how about if you are to store renewables for multi-day, we need storage solutions like batteries at one-tenth the cost of lithium-ion batteries. We don't know how to do that. I know Linda is trying to do that over here with lithium-sulfur batteries. We follow her work very closely, but we don't have it yet. There's still some science and engineering to be done. Small modular nuclear reactors at half the construction cost of today. While all the other cost of energy systems is coming down, nuclear cost, at least in the United States and France, is going up with time. It's not going the right way. So we have to turn that around at half the cost. Refrigerants. This is a very important problem. With the economies growing in the emerging economies, which are mostly in the tropical regions, when people have a little of money in their pocket, what do? And it's 90 degrees Fahrenheit, 90% humidity. What do? They buy an air conditioner. It's natural. You don't want to deny them. But here's the problem. So the demand is going up for refrigeration and air conditioning. The refrigerants that we have today came out of the Montreal Protocol. Hydrofluorocarbons have a global warming potential 2,000 times worse than CO2. Okay? And they'll be phased out as part of the post-Paris Kigali Agreement, Kigali Amendment to the Montreal Protocol. Those will be phased out. So now you've got a demand increasing, and we need new technology. And I'll be talking about this a little bit later. We don't have the technology right now. Okay? We look at zero net energy building. I'm assuming this is maybe some LEED-rated building, and new buildings are all LEED-rated. LEED is all for design, never for actual operation. No one measures to find it. But people are still talking about zero net energy building. Zero net energy building at zero net cost. Now that's challenging. Because if it's not at zero net cost, no one's going to do it. Finally, a big carbon emitter is our industrial heat. We don't know how to decarbonize the industrial heat. Maybe it's hydrogen from the renewables, and then you use hydrogen, but we don't know how to do that yet at scale. We reimagining steel, concrete, and petrochemical processing. These are huge emitters. And finally, food and agriculture sector. If food and agriculture sector were a country, it would rank next to China, US, and then food. That's the amount of carbon emissions that we have in our food and agriculture sector, and that needs to be decarbonized. And if that is not enough, we need a global carbon management at the gigaton scale, which means capturing carbon, storing it underground, harnessing our photosynthetic mechanism of crops and trees to take the carbon, suck out the carbon out of the atmosphere, and put it deep underground so that it doesn't go back. Most of it goes back. And figuring out how to use that carbon-free energy to turn CO2 from a liability to an asset so that you make chemicals and fuels out of CO2. And this has to be done at competitive cost, economic cost, and at the gigaton scale. So we have a gigaton scale problem, 40 gigatons per year. We cannot have megaton solutions in this. We need gigaton solutions. And if you ask the question, how many industries are there at the gigaton scale? There are only 6. It's oil, gas, coal, steel, agriculture, and concrete. That's it. And I tell my friends in the oil and gas industry, since you're already at the gigaton scale, you have this historic opportunity, not a challenge, an opportunity to provide the stewardship. There's money to be made out here. So get prepared for it. So that's what we need to do on the new options and the research. And people get hung up on this amazing renewables revolution, and that's important, but nothing what we really need. What else do we need? This is one part of the insurance policy. These are new options. But in the energy sector, scale is everything. Cost and scale is everything. How do you bring these to scale? Well, the second part of the insurance policy is policy. And that is enabling these solutions, the technology, the solutions to scale with long-term predictable signals. And so what are those signals? What are the policy? Well, one of the things that we are looking at Stanford is, our market designs. Can we design the electricity market, the oil market, the gas market, and a carbon market? We have some of the older statesmen like George Shultz, who was the Secretary of State during Reagan's time. He's 98 years old. He's the most enthusiastic and inspirational guy. And he's proposing a carbon tax, but a revenue-neutral carbon tax, learning from British Columbia. A revenue-neutral carbon tax. What does that mean? You put a price on carbon, the government collects the money from the sources like the oil and gas companies or the coal companies, takes that money, the energy prices may go up because of that, because of the tax, but takes that money and gives it back to the people as a carbon dividend. So people have more money in their pocket, it raises the price of energy, but they're unaffected, so it's not a fiscal drag on the economy. It's a revenue-neutral carbon tax. Wonderful idea. British Columbia seems to have worked. We have been looking at that and said, can we do that in the United States? Extremely hard to do. But we're still trying. This is on the policy side and putting a price on carbon. The second is finance. We need trillions of dollars of low-cost, long-term capital to enable this transformation. And the trillions of dollars has to be low-cost, otherwise, if the interest rate is too high, no one's going to invest. It has to give enough returns. And so at Stanford, we started a sustainable finance initiative to figure out how to evaluate risks. Because if you can evaluate risks, it'll affect cost of capital. So that's the sustainable finance. And finally, while markets are absolutely critical and it's important, there are some things that markets cannot solve. They're market failures, such as in energy efficiency. And we need standards and sensible regulations like appliances. Appliance standards has really changed the ballgame. That's one of the few things that has really worked to make things efficient. Fuel efficiency standards, building performance standards, as opposed to building codes, which is only for the design. performance-based standards for buildings. This is what we need. So I've given you a sort of a broad overview of where we are in the energy sector and what I'd like to do now and what the challenges and opportunities are, not just for our generation, but frankly, for our children and the future generations. This is the challenge you're facing now. And for a scientist and engineer, this is great. Any challenge is an opportunity to do something good that will make impact, positive impact globally. And yes, people are hung up about H-index and how many citations. All that is, that's great. That's good. But at the end of the day, the question is, how can you change the ball game? That's the real problem that I showed. So I'll tell you a few things that we are trying to do. We can't address all of them in my lab, with my collaborators. So I'll tell you a few things that we are trying to do in my lab. So going back to this, I'm going to talk about the refrigerants with zero global warming potential. I'll talk about cooling, given the importance of that around the world. And I'll talk about converting CO2 into chemicals and fuels. This is a major change in my research direction because I got inspired by the problems that we face. So talking about refrigerants, refrigeration and cooling, as you all know, started with, ironically, with heat engines. And heat engines was the beginning of the Industrial Revolution. So you're going back to the origins of the Industrial Revolution because a heat engine, can produce work if you have heat supplied to the engine and it has to dump because of second law, and it produces work, different kinds of work. Or if you put it in reverse, it's a heat pump or a refrigerator. And so on a temperature entropy diagram, it looks like this. You absorb heat from the low temperature and you increase entropy. Then you go up in temperature and you dump the heat at a higher temperature. The entropy goes down. And this is a thermodynamic cycle. This is undergraduate mechanical engineering or physics, right? Chemical engineering. What is not often appreciated is where does the entropy come from? And we normally assume that the entropy comes from the change either from liquid to vapor, that's an entropy change, or compression of a gas, that's an entropy change. And if you go back to the fundamentals, entropy can come from a variety of factors, and that is, I call the diversity of entropy. It could come from the orientation of the dipoles in a material, electric dipoles in a material, internal dipoles. That has entropy. It's called electrocaloric effect. It could be orientational entropy of the magnetic dipoles. That is what magnetic refrigeration is all about. It was invented in the 1930s in Berkeley. And now we have magnetic refrigeration going down to very low temperatures. In thermoelectrics, a lot of people, we have worked 15 years in thermoelectrics. We don't do that anymore. If we talk about the configurational entropy of the electrons in K space, you can compress, you can expand in K space, and that gives you cooling. This is what we normally talk about, configurational entropy of gases, compression. You can have entropy of a redox, electrochemical redox reaction. Most electrochemists don't worry about it, and I'll show you what you can do with it. And finally, any chemical reaction has delta G. Delta G has a delta H, which is the chemical bond, and then there's a delta S in many cases, not all. And the delta S is a part of the redox reaction. So these are all entropy changes that we don't normally think of when we look at cooling. So I'm going to give you an example, and this is kind of the history. If you look at thermoelectrics, this has been a very challenging problem. As I said, we published lots of papers in this, and it is a very hard problem to solve because what we call thermal power of a semiconductor or a semi-metal, which is the S, Seebeck coefficient thermal power, it's essentially the entropy change. Okay? And the entropy change that we measure, the best entropy change in a semiconductor, is about 0.3 millivolts per Kelvin. That's what we can measure. And that's part of the reason, along with other reasons like thermal shunting because of thermal conductivity connections, not the inability to decouple electron transport and phonon transport. All of these things are fundamental issues. But at the end of the day, this really matters, the entropy change. And it's about 0.3 millivolts per Kelvin. So what is the entropy change in what we normally use at scale everywhere in the world is the vapor gas or liquid vapor phase transition. What is the entropy change? We'll know the values from undergraduate thermodynamics, but we normally do it as kilojoules per kilogram Kelvin. How about in a common unit of millivolts per Kelvin? What we find is that, for example, for water, liquid vapor phase transition is 6.3 kilojoules per kilogram. It's about 1 millivolt per Kelvin, 3 times that of that. Okay? And that increases the performance, increases the efficiency. In this case, the design is such you can decouple the cooling part from the heating, and there is no thermal shunt except for some flow in a split air conditioner. And the question we asked is this the theoretical limit? Because it was hard to imagine anything going from a liquid to a vapor and increasing in the configurational entropy, and you're getting more than one. Can this be more than one? So we were exploring, and this is a graduate student came up with the idea who had worked in electrochemistry to look at electrochemical reactions. Now, people knew that there are entropy changes, but no one cared in the electrochemistry world because they didn't care about refrigeration. So we published this paper. I hope it changes. Okay. And this paper is called Continuous Electrochemical Heat Engines. And it turns out that there's plenty of work done in flow batteries where you have a redox reaction of vanadium going from +2 to +3 or +3 to +2, and ferricyanide going from -3 to -4. And if this redox couple, these reactions occur at different on either side of a membrane, and the charge is balanced by proton transport across the Nafion membrane, which is widely known, is off the shelf. And you look at the voltage that you generate as a function of temperature, you get this number. And what you find is that this is not just for vanadium and ferricyanide. There are many other redox couples. And if you look at this combination of -1.4 for ferricyanide and +1.7, if you combine it, you get 3 millivolts per Kelvin. 10 times more than thermoelectrics, 3 times more than liquid vapor. And the question is, what's going on? How can you be higher than liquid to vapor entropy change? And what you realize is that when you put an electron on a redox species or pull an electron, it is not just one electron that you affect. You affect the solvation shell, the water surrounding these redox ions, and you release more than one water molecule, or you collect more than one water molecule, and you get an amplifier due to the redox reaction because of the water surrounding, the solvation on the water. And this has turned out to be, this was serendipitous. We never expected it to be so large, and here we are. Okay? And so there was a paper that we published in Energy and Environmental Science. There's a very nice commentary on that came out in Joule. We're realizing it had the hardest time in the review process because this was different. No one had thought about it. But when it came out, people looked at it and said, oh my God, this is different, and this could give us an opportunity. So this is now going on. We have now reached 20% of the Carnot limit, which is barely possible in thermoelectrics. This is off-the-shelf stuff. And we think we can get to about 60 to 70% of the Carnot limit with this. The other approach that we're taking is electrocalorics. And let me explain how this works. There are materials that have internal electric dipoles, and I'll give you one material that we're using now, if this works. This is a polymer called PVDF, polyvinyl difluoride. And you got fluorine out here, you got hydrogen, you got a huge electric dipole internally. And you can add a few blocks to the polymer to control its Curie temperature and hysteretic losses. And so the way it works is that you have initially the dipoles all randomized in direction. You apply electric field to it, and you align all the dipoles. This is a high entropy state. This is a low entropy state. And when you go from high entropy to low entropy, guess what happens? It heats up. Okay, the energy has to go out. It's like compressing a gas. There, it heats up. So now, with a higher temperature, you can dump the heat to a surrounding, come back to its ambient temperature, and then you let the electric field go, and you randomize, and you expand. That's the equivalent of expansion, but it's orientational entropy, and it cools down. So this is how it works. But then you have to rectify the direction. You can't just heat and cool. So when it is hot, you got to take this polymer and attach it over here. And when it is cold, you attach it to the bottom, and thereby you rectify with a thermal switch. It's like a thermal transistor. Okay? So that's the idea. It just goes back and forth, and it drives heat flow from one side to the other. And so, and the timing, now this is a switch. There are two timings. One is the pulse that you give for cooling, and one is the pulse that you give for mechanical motion. And they better be synchronized. And in fact, we find that there should be some delays because of the thermal time constants and the electromechanical time constants. There needs to be some optimal delays that need to be figured out. And we thought we were the only, so this is, the timing part is very important. And if you do the modeling, you realize that this is the average heat flux. The heat flux generally increases with frequency, depends on the thickness of the film, but it is limited by the contact conductance. I don't know if Mike Ivanovich is out here. He did a lot of work in this. Contact resistance, contact conductance. And but you should be able to get at about 100 hertz or so, you should be able to get about 1 watt per centimeter squared, or 10,000 watts per meter squared, which will be amazing. That's equivalent to the thermoelectric cooler, but it'll be much more efficient. And so this is the theory. This is the experiment. This is actually that flipping going on of the little element. And these are actually, the red is the cooling, and the black is the heating. So cooling and heating going on. And this is at 1. So this is above that is heating, this is cooling. And this is at 1 hertz, 0 delay. This is 50 millisecond delay, and you get much better performance. We thought we were the only ones. We got scooped. That's okay in the big scheme of things, by another group that developed, and they produced 300 watts per meter squared, which is not bad for the first time. But the COP, the coefficient of performance, was 13, which is absolutely spectacular. The normal refrigerator that you have in your home has a coefficient of performance of around 5 to 7. This is double that. And so we are now at 400 watts per meter squared. I think we can easily go beyond 1,000. That's where we're going right now, and we'll publish this work thereafter. So this is good. This is the kind of thing that we are involved in cooling. And what we think could be done with this thing is that you can make plastic sheets like Saran wrap, and you can make sheets like this. And we think that could be quite interesting for wearables. If you want to cool down yourself, do you really need to cool the whole room? Or can you cool it just to your body? And if you're at 90 degrees Fahrenheit and 90% humidity in Chennai, in India, a little bit of cooling may not be a bad idea for you, just to get you a little comfortable. You can increase the set point of your air conditioner to a higher value, and that saves a lot of energy. And in fact, after Fukushima in Japan, what people did was that, okay, let's take our suits off. You don't have to be formal anymore because we don't have electricity. And we raised the temperature set point of your air conditioner to about 25 degrees. With a suit, it's uncomfortable. With shirts, it's not uncomfortable. And they saved energy. A 1 degree set point has a huge impact on energy. So this is another, we think this could be quite interesting. Let me give the final part, is the redox heat engine. Again, this is all heat engine based. Can we dissociate CO2 and water? And the way we are approaching this, not electrochemically. Most people are doing electrochemically. But most of the chemical industry today is not electrochemical, it's thermochemical, almost exclusively. So we said, if we can figure out a process or materials that you can do thermochemical dissociation of water and CO2, the industry knows how to scale. We don't have to worry about scaling. We don't have to worry about cost because they know how to do it. And so it works like this. You take a metal oxide and you heat it at a higher temperature to get the oxygen out. And then you take this oxygen-deficient metal oxide, expose it to water and CO2, and if it's designed the right way, it'll grab the oxygen to produce hydrogen and CO and goes back to metal oxide, and you have to dump some heat. So that's the idea. Each of these reactions, these are reactions, have to be delta G less than 0. And as you can see, the only variable between the two out here is temperature. Okay? That's the only thing that changes, which is a heat engine. So if you plot delta H and delta S, you get graphs like this, delta H versus delta S. And anything above this blue line, this is for the lower reaction, anything above the blue line is possible, delta G less than 0. Anything below the blue line, delta G greater than 0, it's impossible, thermodynamically impossible. Same thing for the red line. Anything below the red line is possible. Anything above the red line is impossible. So if you want to have a material that can cover both reactions, you're left with this thermodynamic sweet spot. And as you can see right away, that you want as high a delta S so that you can get to, bigger part of the sweet spot. So the question is, how do you change delta S? Again, all goes back to the entropy. How do you get delta S to be high in a solid material? Okay. So we have been looking at a variety of materials, and I'll give you just one example. These are ferrites, spinel ferrites. Spinel is a certain crystal structure. This is a iron, and because of the ferrite, that's what we call it, a ferrite. And this M, which are these dark brown boxes in the tetrahedral crystal site, that can be magnesium, cobalt, nickel, manganese, etc. And the iron is both at the tetrahedral and the octahedral site. And so this is your spinel structure, and you can find which species, if you've got iron and cobalt, both are transition metals, both can be active in a redox reaction that I just described. The question is, which one is redox active? Are both active or one of them? You can identify that with synchrotron radiation, X-ray radiation, because the X-ray radiation, there's a shift because of oxidation state. And so what we found in the spinel ferrites is that when you look at the shift for both iron, nickel, cobalt, you find that iron is the redox active species, and the nickel and cobalt is the redox inactive species. So you can add magnesium and it still works. Magnesium is not transition metal. It still works because iron is doing the job. So the conventional wisdom in the field was that, if iron is the redox active species, why don't we increase iron to make it more and more active? And what people found was that it does not make it more active. And we, being naive and new to the field, accidentally, serendipitously, we sort of made things that are iron poor as opposed to iron rich. And what we found was that the iron poor ferrites had 5 to 10 times the CO2 dissociation capacity, not only with ferrites, but all state-of-the-art materials. So this is, let me just show you this one. This is the carbon monoxide yield from CO2 to CO. This is look at the red ones, which are CO yield. And these are the thermodynamic limit of cerium oxide, some perovskites. And this is the spinel ferrite. These are the numbers that we get from, this is spinel ferrite. You go down in iron concentration, and the capacity jumps up by a factor of 5 to 10. And we were just completely flabbergasted by this, what's going on? Because this is not your traditional conventional wisdom. And what we found, to our surprise, that the delta S in these materials changes because of a phase transition. So when you have iron poorness in the material, it induces a phase transition because it introduces a different phase of a ferrite inside the spinel. And if you take out iron, you create what is called a rock salt structure along with the spinel. And when you change the temperature, the rock salt structure grows. When you reduce the temperature, the spinel phase grows and the rock salt reduces. And a phase transition, just like liquid vapor, this is solid-solid phase transition, has a much higher delta S than anything else. in a solid phase. So we are, and this is now the phase diagram. We can actually, these are some of the predictions, this is the experimental data, and we can see the rock salt in the spinel phase swinging with X-ray. Now we have looked at resonant X-ray to find out where these ion atoms are, octahedral, tetrahedral, as well as what's the redox state of these ion atoms, etc. So anyway, so this is, I just wanted to give you a few examples that we are trying to do. There's a lot more work to be done. I just want to remind people of all the things that are remaining, and this is really needs to be done so as to really solve this simultaneous global and energy and climate equation. Now, when you look at this, people get pessimistic. I get pessimistic once in a while that, oh my God, this is a huge endeavor. But when you look at the science, you get optimistic. But a lot of people are naysayers. They said, oh, we might as well get ready for 4 degrees Celsius. If 1 degree, the tail is so bad, you can imagine what the 4 degree is going to be. Okay? And there are a lot of naysayers. And I just go back in history and look at predictions by very famous people of what those, what the naysayers actually said. The first one is, these are infamous or famous predictions of the past. The first one is Lord Kelvin, who in the 1890s said, radio has no future. X-rays will prove to be a hoax, and heavier than air flying machines are impossible. Lord Kelvin was very opinionated, but he was dead wrong. Because you never consider the laws of physics, that whether these things are violating the second law of thermodynamics or the first law. Okay? And of course he was wrong. But he was convincing enough that he convinced one of the Wright brothers, Wilbur Wright, in 1901, who said man will not fly for 50 years. He just followed Lord Kelvin. Fortunately, he had a brother. And in 2 years, they showed the existence proof that it can fly because the existence proof already happened in nature. So I think the best way to predict the future, as long as you satisfy the laws of physics, the best way to predict the future is a statement by Arthur C. Clarke: any sufficiently advanced technology cannot be distinguished from magic. And it's really for the students out here to do that, to show some magic in the world in the future. Thank you.
Thank you so much.
Thank you so much, Arun. It was really a magical journey for us in understanding energy and climate equation. So we'll open up for a couple of questions if we have an audience before we move to the break. Any questions? Yes.
I have a question. This example that you were just giving, is the potential for thermal batteries?
It is a thermal battery.
I mean, as opposed to chemical batteries as a solution to storing renewable energy.
Right, so if you look at that oxide and you heat it up and the oxygen comes out and you keep it in an oxygen-free environment, that is a thermal battery, because when you introduce oxygen, it grabs the oxygen, produces heat, and it gives the heat back. So it's thermal storage.
And is that a cost-effective?
It is, so a lot of people are looking at thermal storage as a way to store electricity, because you can run a heat pump. This is basically a heat pump if you run it in reverse, or you can run it an engine and thereby store electricity that way. We desperately need thermal storage at high density. This is very high density storage compared to storing it in water, which is sensible heat, or in steam. Because if you store it like this, it is insulation-free thermal storage. You can get rid of the oxygen and then bring it down to room temperature, keep it outside without any oxygen, oxygen-free environment, and you can you store the heat at room temperature as long as there's no oxygen. You introduce oxygen to it and it heats up again. So chemical reaction have not really been used for thermal storage. There's a very interesting chemistry, got a Nobel Prize, called Diels-Alder chemistry. Diels-Alder chemistry, I don't know how many of you are familiar with Diels-Alder chemistry. You add heat to it, enthalpy to it, and you take two species and you separate them, dissociative chemical reaction, both of them still in liquid phase. Okay, and they can phase separate. And you can keep it like that, and you've just stored heat, the enthalpy, without a requirement of insulation. You bring them back again with a catalyst, and you got your heat back. So that's insulation-free thermal storage. It would be really interesting. A lot of chemistry involved in that.
Questions or comments?
Yep.
Hi. Thank you for your talk. So Japan is going to use the 2020 Olympics as a platform to showcase the potentials of a hydrogen economy. But I saw that it was conspicuous by its absence in your talk. So I would like to know your thoughts about how it might be a paradigm or may not be a paradigm change in the energy economy.
I mean, I talked about hydrogen for decarbonizing the oil and gas, petrochemical industry and the steel industry, et cetera. The question is, where does hydrogen come from? Today, most of the hydrogen is produced from methane, steam methane reforming, and it has CO2 emissions. And if that's the case, I'm not exactly sure what it'll do to the CO2. For a lot of people look at hydrogen economy for transportation, and Toyota is big on this, Mirai, et cetera, fuel cell cars. And that's all fine. The question is, how do you distribute the hydrogen as opposed to distribution of electricity? And I think it's going to be very regional. So in Japan, they may put a hydrogen distribution infrastructure. In Europe, Shell is already doing that. And it's putting hydrogen filling stations, which is great. It's a chicken and egg story. Will the cars come first? Will the infrastructure be built? And someone has to disrupt it in some way that you break the chicken and egg logjam. And sometimes the government do it, sometimes some companies do it, sometimes the partnership between an auto company and an oil and gas company does it. So I think hydrogen should be there. I mean, you got a lot of renewables. If the hydrogen comes from renewables by electrolyzers and you produce hydrogen, that's fine. That would be perfectly acceptable. But I think today, hydrogen is a $100 billion industry. We produce about 50 megatons of hydrogen, and that is mostly used for ammonia synthesis, for fertilizers, and in the petrochemical industry for cracking long-chain hydrocarbons. I think that's the first use. If you can decarbonize that industry, that'll do more for solving the global, the simultaneous equation than for, frankly, the transportation sector.
Question.
So first of all, I would say that I never look at things in the terms are interdisciplinary, multidisciplinary. There's a problem to be solved. And can we solve the problem? And if you need physics, if you need biology, if you need sociology, let's put that all together to solve the problem. That's the way I look at things. The other way, so let's break down silos because you really have to solve the problem. Okay? The other way to think about it is, which I think is a big mistake that people have made, at least in the United States, is the Vannevar-Bush model. Do you know how many people know about Vannevar-Bush? He helped the United States during the war. He created the National Science Foundation and everything based on his vision after the war. So his model, I mean, he had huge contributions to the United States. His model is that there's basic and there's applied research and there's engineering, there's technology, and you hand off. That's all wrong. Because the way progress is made is that you blur the boundaries between science and engineering and you create feedback loops. You create teams of fundamental scientists, okay, basic science, fundamental looking at exploring things with engineers who can take the discoveries and turn them into this. But when you make a system out of it, you realize more science needs to be done. You go back to the science, and that feedback loop is very important. And that's one of the things, ARPA-E, that you mentioned, was created. Because in the Department of Energy in the United States, you're siloed. You've got the Office of Science, and you've got the Applied Energy Office, and very little talk between. So RP said, we'll just ignore all these boundaries. We'll say, we're going to solve some problems, and we will put scientists and engineers together. And if we go back to one of the most innovative places the United States ever had in terms of science technology is the Bell Labs. Without Bell Labs, we won't have any of this out here. And wireless communication, cellular communication, satellite communication, optical fiber, all of this came out of Bell Labs, right? Unix, you name it, C, all of this, speech recognition. You think about Bell Labs, and one of the things was they ignored these boundaries, and they created the whole information revolution in a matter of 40 years, which is amazing if you think about it. So that's the lesson learned in history, is that when you try to create silos, things break down. Okay? The baton is never passed. And you really want to break down the silos and put science and engineering, blur the boundaries. Are you a scientist or an engineer? You're probably both. You do both. And I think that's the lesson learned. That's a long answer to a short question. But as you can see, I feel very strongly about it.
There's one more question.
I wanted to ask about, like, you mentioned the cost of wind and solar underpinning unconventional fossil fuel technologies. So how much of a potential do you think is there for further investment in those fuels to solve some of this emission problem?
Yeah, so I think this is all good. Imagine if today we're trying to solve the simultaneous global climate and energy equation, and we didn't have solar and wind. That would be a real disaster. So we have this. It's not enough, but the question is, can the cost come down even further? Absolutely. Today, business contracts are being written for solar at 2.5 cents a kilowatt hour, which is amazing. And the game is really in the efficiency of the solar cell. If you can go up, and people are working on perovskites and all, which is wonderful, but tandem cells at low cost, manufacturing cost, would be terrific. Why efficiency? Because most of the cost today is not in the panel. The panels are 25 cents a watt. Most of the cost is in the installation. So if you make it more efficient, you have to install less. People are now putting solar farms with solar panels facing both sides of the panel. Okay? One's facing the sun, the other facing the ground, and they paint the ground white so that it reflects. So you install less. Even though it's not getting the full sunlight, you're saving on cost. So those are engineering innovations, but scientifically, if you can increase the efficiency of solar cells without increasing the manufacturing cost of the panel, good to go.
Let's thank the group.
Thank you.
We have a small token of appreciation from Win, where you all will be in our Hall of Fame.
Okay. Well, thank you very much.
Thank
Appreciate
you.
it. Yeah.